All right, so this is the last section of chapter 14. And just like 14.7, we're still working on optimization problems, but optimization problems of a specific type. So back in section 14.7, the previous section, one of the examples we looked at was minimizing the surface area of a box with a fixed volume of 1,000 cubic centimeters. That volume is computed by multiplying length times width times height, which we were representing by x, y, and z. So we could think of that as subject to, we were minimizing the surface area of a box subject to this constraint, x, y, z equals 1,000. Surface area is a function of x, y, and z. It's s equals 2xy plus 2xz plus 2yz. And we use this constraint to make a substitution to reduce this function down to one of only two variables. But there's an alternative way of approaching this that doesn't require a substitution the way that we did it in the previous section. Instead, what we're going to do is let me back this up. So this is a common thing that we want to do in optimization problems. We're given a function that we want to optimize, but we don't want to just optimize it for all possible choices of x, y, and z. We want to optimize it subject to a specific constraint. X, y, and z have to be related by a constraint if they're allowed to be used in this function. So a general case is optimizing a function of the form f of x, y, z subject to a constraint of the form g of x, y, z, some other function of x, y, z equals a constant. That's what we have here. G of x, y, z equals a constant. And we're maximizing or minimizing, in this case, this, which would act as f of x, y, z. Now, the way we're going to approach this in this problem requires us to use a little bit of our knowledge regarding the gradient vector. That's kind of the technique, the concept that's at the heart of this. So before we go on to maximizing functions of these types, we're going to simplify this concept by looking at functions of two variables instead of three variables to get a sense of how this method is going to work. So that is, we're going to try optimizing a function f of xy subject to a constraint of the form g of xy equals k. Now f of xy is a function of two variables. That means graphically it would represent a surface in 3 space. G of xy equals k. By setting this equal to k, what we're actually looking at is an equation in two variables set equal to a constant. That would determine a curve in the xy plane. Now, we can compare these two things by taking the surface, f of xy, and graphing its level curves. So we talked about level curves back in the beginning of this chapter. And remember, that's just all the curves that are a set of curves that we obtain by setting f of xy equal to specific constants. So here's an example of what that might look like. These red curves are the level curves, or a sum of the level curves for the function f of xy. So if we set f of xy equal to 7, that might determine this curve in the xy plane. F of xy equals 8 might determine this curve, and so on and so forth. Looking at those red curves, if you try to picture what the surface of this function would look like, because these numbers are increasing, those correspond to the z values of the points that lie on the actual surface given by f of xy. And looks like as we go from this sort of outer level surface towards this inner one, the z coordinates of those points are increasing. So it looks like we're going uphill as we go this direction. Okay, so, or in other words, our function is increasing as we move towards those inner level curves. Now, our constraint, g of xy equals k, again, is a curve in the xy plane. So it might look like this blue curve as an example. And this is a constraint on our function, which means we're only allowed, for the purpose of this optimization problem, to plug in values of x and y into our function f that live on that blue curve. We can't plug in this point because it's not on the blue curve. We can only plug in these points. So of the points that are on this blue curve, which one maximizes or appears to maximize f of xy? Well, it appears to be this point because, again, f of xy appears to be increasing as we go this direction. Imagine this is going uphill and we're just looking at it from the top down. That means that this blue function, or this blue curve, when those points are plugged into our function, are going to give us a space curve that sort of climbs up this hill, if you will, comes to a high point, and then turns around and comes back down the hill this direction. Okay? Again, think of this as looking from the top down at a hill that's going uphill this direction. So that appears to be the highest point. But there's something else that I notice about this. The blue curve appears to be tangent to this specific level curve, where f of xy equals 10 for this example. And it sort of makes sense if you think about it, based on how we're interpreting these level curves, that that's what you would want to look for in the general case. Where is the curve given by this constraint going to be tangent to some level curve of the function f of xy? Or another way of saying that, at what point will my constraint curve have a common tangent line to a level curve of f? If you can find such a point, not only will the level curve and the constraint curve have the same tangent line, but by default they would also have the same normal line, the line passing through both of those curves perpendicularly. Why would I care about the normal line? Well, remember, one thing that we determined back in 14.6 is that if you have a tangent vector to a curve, and it's whether it's a space curve or a plane curve, this is still true, the gradient vector of that curve at that point, or of that function at that point, will be orthogonal to that tangent vector. That means that the gradient vector of g and the gradient vector of f will be parallel to each other. They're both lying along that same normal line. They're not necessarily equal, but they are parallel. And what that means for us is that I should have gradients in here. I should say gradient. That should be the gradient of f there. I missed the del operator in there. The gradient of f of x naught y naught, if this point is x naught y naught, should be equal to some scalar. There's a lambda in there, a Greek letter lambda, some scalar multiple of the gradient of g. Okay, because that's what it would mean for those two things to be parallel. If we generalize this argument into functions of 3 variables, then we could follow similar logic. Instead of level curves, we'd be looking at level surfaces. And I'd be looking for where the constraint surface is tangent to a particular level surface of f. I'm not going to attempt to draw anything like that, but the underlying logic is really the same. In that case, the gradient vectors of both f and g, which are now functions of 3 variables instead of just 2, would also be parallel, meaning that they're scalar multiples of each other. That lambda, that Greek letter lambda that's showing up as the scalar here, is what we call a Lagrange multiplier. And that leads to this technique that we call the method of Lagrange multipliers. So what is the method of Lagrange multipliers? What we want to do with this method is we're aiming to find maximum and minimum values. And based on this logic, we would expect those maximum or minimum values to occur wherever the gradient of f is equal to some scalar times the gradient of g. Now there is a condition. We need the gradient of g to be non-zero, and we're not going to go into detail as to why that's the case. There's a more what we're doing here is we're coming up with this method using intuitive logic. We're kind of arguing from intuition. I didn't give you a formal proof of why this works. Your textbook goes into a more accurate proof, which we're just not covering for the sake of time. It's not difficult necessarily, but in that argument they explain why del g can't equal 0. We're not going to have to worry about that for the examples what we do. But anyways, if you have a function f of xyz and it's subject to a constraint g of xyz equals some constant k, if a maximum and minimum value exist and del g is non-zero, then we get this. In order to find the values of x, y, z, and lambda such that this equation is true, as well as this constraint, what we do is we evaluate f at all of the points x, y, and z that result from these equations. So there's a lot of algebra that's going to follow from these equations, as you'll see. The largest of those values is the maximum value of f, and the smallest is the minimum value of f. Kind of like how we used the extreme value theorem in the previous section to come up with a bunch of candidates for minimum and maximum values, and then we just compared them and picked the smallest one to make that our minimum, pick the largest one to make that our maximum. So it's difficult to see how this works just based on this description. You need to see a couple of examples to make sense of this. So let's start with this first example. I want to find a maximum and minimum value for this function, f of xyz equals e to the xyz, and it's subject to this constraint, okay? 2x squared plus y squared plus z squared equals 24. All right, so we have f right here. And I know from my gradient, if I were to evaluate the gradient of this function, I'm looking for the partials of this function with respect to x, y, and z. I'm going to write all of those out separately. Fx is going to equal, this is pretty easy to do partial derivatives of, yz e to the x, y, z. Fy would equal xz e to the x, y, z. And fz is going to equal xy e to the x, y, z. Those are easy partial derivatives to do. Next up, what is g? Well, according to this, g of x, y, z, which comes from my constraint, is just this part. It's the part on the left side of the equal sign, because remember, we're looking at a constraint of the form g of x, y, z equals a constant. So g of x, y, z is just 2x squared plus y squared plus z squared, and we need the gradient of g as well. And I'm not going to write it in the form of a gradient, I'm just going to pick out the components, the partial derivatives. Gx is equal to 4x. Gy is equal to 2y. Gz is equal to 2z. Those are easy partial derivatives to do as well. Okay? Now, if this equation is to be true, then I should be able to equate the components of these two vectors. So in other words, fx, which would be the first component of the gradient of f, should be equal to lambda times gx. You got that? So we can write fx equals lambda times gx. And fy, similarly, should be equal to lambda times gy. Fz is equal to lambda times gz. We're going to basically set up a system of equations using these. Now that lambda, that Lagrange multiplier, in a lot of the cases when we're working out examples like this, we never end up solving for it. Because we oftentimes don't need it. It ends up canceling out in the process. There are some cases where it's beneficial or even necessary to solve for lambda, but just, again, most of the time we don't need to. Okay, so let me set up this system of equations now. Fx, which is this, equals gx times that lambda. That's going to look like yz e to the xyz equals 4 lambda x. And then fy equals lambda times gy. Xz e to the xyz equals 2 lambda y. And then we got xy e to the xyz equals 2 lambda z. All right? Now, what I want to do is treat this like a system of equations. And initially it might look like a very difficult system of equations to work with, but I notice something. All three equations have something very important in common. They all have the same exponential. So if I isolate the exponential in each one of these, I can write this as e to the xyz equals 4 lambda x over yz, and e to the xyz equals 2 lambda y over xz, and e to the xyz for the final one equals 2 lambda z over xy. By doing this, all three of these are the same. That means I can equate any pair of these that I want. All three of these should be equal to each other. And that helps a lot when trying to solve for x, y, and z. That's the goal, is we're trying to solve for x, y, and z in this system. So let me set these two equal to each other. 2 lambda y over xz equals 2 lambda z over xy. And by doing this, a whole lot of stuff cancels out. The 2 lambdas cancel out. The x's cancel out. And I have yz equals, or y over z equals z over y. Cross multiplying shows me that y squared is equal to z squared then. Okay? If I take square roots of both sides, that tells me that the absolute value of y is equal to the absolute value of z. Okay? So y and z might be equal to each other, or they might be opposites of each other. Either of those are acceptable. So that's pretty cool. Now let's see if we can do something with the x. So let me go back to my original system of equations and maybe equate this guy to this guy. So that's going to tell me that 4 lambda x over yz is equal to 2 lambda y over xz. And then again, some stuff will cancel out. So I can cancel the lambdas, I can cancel the 2 and make that a 2. I can cancel these z's. And what I have now is 2x over y equals y over x. Cross multiplying in this case gives me 2x squared equals y squared, which implies that root 2 times the absolute value of x equals the absolute value of y. Now, these I'm not going to actually need so much as these, because even though I'm trying to solve for x, y, and z, these equations are a little bit nicer. Notice that 2x squared is equal to y squared, but the same y squared is also equal to x squared. So I could write that 2x squared equals y squared equals z squared as kind of one big equality. Now, where do I get to use those? Well, remember, any ordered triple x, y, z has to also satisfy this equation because this constraint has been placed on our function. So notice I have a 2x squared plus y squared plus z squared there equals 24. And according to this, y squared and z squared are both equal to 2x squared. So I can find the y squared and the z squared here, substitute a 2x squared in for those. That's going to give me this. 2x squared plus 2x squared plus 2x squared equals 24. That's 6x squared equals 24, or x squared equals 4. In other words, x, the absolute value of x, equals 2. Okay? Or another way of saying that is x equals plus or minus 2. All right? But if that's the case, I can use that to solve for y and z. Because if I plug a 2 into the x here, plus or minus 2, I'm going to square it, it's not going to matter. I get 2 times 4, which is 8. Y squared is equal to 8, so that y is equal to plus or minus root 8. So y is equal to plus or minus root 8. And then z squared is equal to y squared, so the same is true of z. Z is equal to plus or minus root 8. All right, now this actually gives us a ton of different combinations. For example, xyz, the point xyz could be 2 root 8 root 8, could be 2 negative root 8 root 8, could be negative 2 negative root 8 negative root 8. You can see where there's a lot of combinations. But what are we doing with those numbers? We're plugging them into our function f and seeing which combination gives us the largest number from this function and which one gives us the smallest. And even though there's a lot of different combinations that I could use, there's actually only 2 different values that I'll ever get from those different combinations, because the only thing that's changing in each of those combinations is the sign of these numbers. The 2, the root 8, and the root 8 aren't changing, it's just the sign. So really what matters is whether this exponent comes out positive or negative. Let me take a look at one case where we would get a positive. That's going to give us a maximum value. So for example, if f of x, y, and z, if I use the 2, root 8, and root 8, that would equal e to the 2 root 8 root 8, which is 2 times 8, or 16, e to the 16. That gives me a positive exponent up there. That's going to be the largest exponent that I could get. So that would be my absolute maximum for this function. Let's find a minimum next. Okay, if I make one of those things negative, say negative 2, I'll leave root 8 and root 8 alone, then because I'm taking the product of these 3 numbers in the exponent, Negative times positive is negative. So that's going to become e to the negative 2 root 8 times root 8, which is e to the negative 16th. And that's going to give me the smallest possible value. Hopefully you can see why using different combinations of plus or minus 2, plus or minus root 8, plus or minus root 8 won't give you anything different than e to the 16th or e to the negative 16th. And just by comparing these, this is clearly a much larger value than this is. Okay? So that's the Lagrange multiplier method. We're going to do one more example, but we'll do that in the next video.